Welcome to the presentation, How to Maximize Spatial Presence, Design Guidelines for a Virtual Learning Environment for School Use. In this presentation, we will first address VR use in schools, then discuss methodology, and then present selected results. The use of VR in the school classroom is still in its infancy. In contrast to general learning mechanisms, there is little research on the practical use of VR learning environments in schools, the design of VR learning environments for use in the classroom, and how learning with VR can succeed during the school day. We focused precisely on this gap and designed a research project that explored the use of design principles of VR learning environments with students in school. An important goal here is that the full potential of immersive learning can be realized. A crucial factor for this is a high spatial presence experience, which can be best built up in a highly immersive geo-environment. Design-based research, or DBR for short, was chosen as the methodology. Design-based research offers many advantages that are useful in generating design principles. By applying that theory during the design process and the DBR typical microcycles, an in-depth investigation can take place. The research objective is to generate design principles for everyday relevant educational problems, which in our case is the implementation of a VR learning environment. The study was conducted at a German high school with 4 10th grade classes and a total sample size of 102 students. The following research questions were formulated. Which design principles must be followed to design an out-of-school learning space as an immersive virtual reality environment? Which general design principles can be derived from these findings? The microcycles were planned sequentially in order to increase the authenticity of the environment piece by piece and to investigate the components relevant for a VR learning environment such as space environment, movement radius, and ambient sounds with regard to their interaction with the spatial presence experience. The applied scales can be seen below. The scales of current motivation, spatial presence experience, and realism were collected across all microcycles. For the learning stations, perceived learning effectiveness, the VR scale, and perceived ease of use were added. First, I quickly explain how the formation of spatial presence experience works. Spatial presence experience is not a fixed state, but can be influenced in every second of VR use. This happens via different factors, such as the involvement and the spatial situation model, which influence the so-called hypothesis test. This test decides whether we accept VR as a new reality or not. The user spatial situation model is formed mentally and shows whether the user was able to mentally grasp the virtual space. As a designer, it is possible to influence some of these processes to favor the formation of the presence experience. In microcycle 1, we surveyed the first prototype of the base environment and the realistic implementation of it. It turns out that the suspension of disbelief subscale exerts a direct influence on the hypothesis test and thus presence experience. It asks, for example, whether it is necessary to concentrate on actively blocking out disturbing stimuli. The visual spatial imagery and attention exert influence on the spatial situation model. The value of the spatial presence experience is already quite high, but still expandable. The environment was redesigned based on qualitative feedback and to further enhance the presence experience. After redesigning the environment, the range of motion was examined in microcycle 2. Groups of 2 on 2, 4 on 4, and 6 on 6 meters were formed. Path analysis showed an undesirable effect of suspension of disbelief in the 2 on 2 meter group and no significant effect in the 6 on 6 meter group. On the other hand, the 4 on 4 meter group showed a dominant influence of the spatial situation model on the presence experience. It was continued with the 4 on 4 meter radius due to several factors such as the space requirements in schools and the good values of the presence experience. In microcycle 3, realistic ambient sounds were added. There was no effect to microcycle 2. The path analysis as well as the subscale scores showed no significant change, only descriptive increases in the subscales. In the first learning station, the students had to assemble a floating chamber. It was used to measure the CO2 outgassing of the virtual river. The evaluation of the data from the first learning station showed some significant increases in the subscales. Fuzz analysis showed that visual spatial imagery and attention allocation had a significant effect on the spatial situation model, which in turn had a positive effect on spatial presence experience. In the second station, the students were able to influence the virtual environment. They used 4 levers to control the factors that favor CO2 outgassing. Using a chemical magnifying glass, they were able to visualize the invisible CO2 at the particle level. The path analysis of the second learning station showed similar values as in cycle 4. The presence experience also slightly decreased descriptively. At station 3, the students were able to make a tree hologram H and read off values about its CO2 storage. These had to be transferred to a pinboard. The values of station 3 were similar to those of cycle 4 and 5. There were hardly any noticeable changes. What stands out in particular is that involvement was greatly increased, but it had no effect on the formation of the presence experience in the path analysis. This leads to the next design principle. Due to the medium correlation between involvement and the experience of spatial presence, but the lack of influence of involvement on the formation of spatial presence experience in realistic VR learning environments, the experience of spatial presence and involvement should be planned separately but aligned. These results allow for the formation of additional design principles. Larger radii of motion should be preferred to enhance the experience of spatial presence, but the designer should always consider the spatial constraints of the deployment site. To plan and design realistic VR learning environments, visual, auditory, and kinesthetic cues should be adapted to the realistic environment. I hope you enjoyed this presentation. Thank you for listening. Further information to this study can be read in our TVCG paper.